okay, let's take a look at some of the properties of writing up our one-way ANOVA or one-factor ANOVA F-test if we're looking at the equality of means. Now, the null, we're back to some equal signs. I know in chapter 11, towards the end of chapter 11, when we were running the independence, chi-squared independence, we had words in our nulls. We're back to just symbols, right? We got our means, we've got our K, our level of our factor. So we have a K level for our factor. So we have K groups. We're going to say all of the averages are equal. So that's the null here, that every average between all of your groups, it's all the same. Now this F-test statistic, it's going to be a good time. It's a ratio. It's the mean squares between and ratio to the mean squares within. Now I'm going to talk a little bit later, just down the page here, about these mean squares. These are some fun statistics to crunch. They take a lot of calculation. All right, it's a little bit obnoxious to try and calculate this. And the idea here, though, is if the null were true, right, which is the thing that we're always assuming, this ratio, just to give you some perspective, should be close to 1. So if the null is true, this number should be close to 1. All right. The further away this test statistic is from 1, the more evidence we have against the null. So we're looking for an F-test statistic close to 1. Now, that might change a little bit slightly depending on your degrees of freedom and things like that. But close to 1 is a pretty good bet that the null is true, or that we're going to fail to reject the null. Now, the alternate, it's written a little bit, it's got some words, and it might seem a little convoluted, but let's talk about it. It says at least 2 of the group means are not equal. So if the null is that all of these are equal, again, the complement is that they are not all equal, right? And when it's not that, I shouldn't have underlined the word not. I want to emphasize the word all. All right. So if the complement is that they're not all equal, it could still be that mu1 equals mu2, and maybe mu2 equals mu3, but maybe mu3 doesn't equal mu4. So they're just not all equal to each other. So that's why I'm saying at least 2 of the group means are not equal. It could be that none of them are equal, but we're just saying it's not all that are equal to each other. That is the complement here. So what I'm trying to say here is, let's say you had H naught, mu1 equals mu2 equals mu3 equals mu4, right? It could be that mu1 equals mu2 equals mu3, and that does not equal mu4, right? So the null would be wrong. It could be that 2 of them are off. It could be that all of them are off from each other. You don't know how far off they are. You just know that they're not all equal. So that's what we're talking about when we talk about the alternate. Now, much like chapter 11, when we get this test statistic, it's going to be positive, all right? So we're only ever going to look at right-tailed tests. So to calculate that p-value, we want the area under the F distribution. We're going to pick up a new graph, and we're going to go to the right of the calculated F test statistic. Now to do that p-value, right, we have capital P, F greater than your number. We're going to use FCDF, low, high, and in the F distribution, there's 2 degrees of freedom. And I'll give you the formulas below. There's the degrees of freedom between and the degrees of freedom within, okay? All right, now for assumptions, let me scooch this up. All right, so we have some assumptions in view. All right, assumptions. The observations are obtained independently and randomly from populations defined by the factor levels. All right, so we need independent random samples. Okay, great. The population at each factor is approximately normal. Here's our deal breaker. All right, and then the normal populations have a common variance. And we've talked about variance before, right? Variance is the square of standard deviation. So as long as they have a common variance, we can go forward with this. Now there are some rather annoying calculations that must be made to calculate this test statistic. All right, we'll use our calculators in class, but I feel as a stats teacher, I should at least write them out for you in the formulas, and we're going to take a look at them, okay? All right, so let's take a look at these formulas. Oh, look at what a good time these formulas will give you. All right, so if we have our levels here, all right, n sub j is the size of the jth group. So there were, in this case, n sub j, or I should say in example 1, n sub j would have each been 6 because I had 6 Hondas, 6 Corollas, and 6 Nissans. And it's not the case where you always have to have equal numbers in each group. I mean, you use whatever you have available to you. All right. So, and then SJ will be the sum of the values in the jth group, and N will be the total number of all combined data values. So we've talked about K and N before. We haven't really talked about N sub J and K sub J before. All right, so here's some formulas you're definitely going to need. You're going to need your 2 degrees of freedom formulas. So the degrees of freedom between are K minus 1, and the degrees of freedom within are N minus K. And when we talk about between, we're saying between the various groups. So that's what that is referencing. So I'm talking about what are the degrees of freedom between the Hondas, the Corollas, or I should say the Hondas, the Toyotas, and the Nissans. And then this is within, it's just saying what are the degrees of freedom within any one group. So what's the degrees of freedom within the Toyota group, within the Honda group, and within the Nissan group. So you see me pushing my pencil horizontally, so between the groups and then within any one group. I usually go vertical when I'm talking about them. All right, we need to get to this test statistic, which is down here. You got your mean squares between and your mean squares within. So your mean squares between is this ratio of something called the sum squares between to the degrees of freedom between. So let's try and unpack sum squares between. It is a good time. All right, so the first thing we have to calculate is the sum squares total. So we're gonna sum up all of our values, all of our data values, and we're gonna subtract out that sum divided by n. So that's the sum of the squares. So when I say SS, again, that is sum of squares. And that's what you see right here is a sum of the square of every value we have. And this would be, if we were doing example 1, this would be for all 18 cars. So I add up all of their gas mileages, or I should say I add up the squares of all of their gas mileages and divide out that ratio. All right, now the sum squares between, okay? So this is what we're gonna do. We're gonna take our sum of all the values in one group, square it, divided by the number of, well, I should say the number, I was gonna say number of cars because I was doing it like example 1, but the number of observations in that group. We're gonna add all of those numbers up. We're gonna subtract, oops, I messed that up, sorry. We're gonna take the sum of the values in the jth group squared divided by n sub j, and then we're gonna subtract out, this one's fun, the sum of just the numbers, all of that, square that in total divided by n, and then we're gonna add up all of those differences. So this is a good time. I'm telling you, to calculate these test statistics, there's a lot of number crunching that goes on. So that's the sum of the squares between the groups. And why we're saying between the groups is because each time J swaps out, if I was doing it again for the car example, we're gonna calculate this number for the Toyota cars, then we're gonna calculate this number for the Honda cars, then we're gonna calculate this number for the Nissan cars, and we're gonna add those 3 numbers up. So that is the sum of the squares between. Then we're gonna find the difference between these 2 numbers and get the sum squares within. All right? So like I said, buckle up, it is a good time. Once you get the sum squares between and the sum squares within, you're gonna put them in ratio to your degrees of freedom, and we're gonna get our mean squares between and our mean squares within, okay? And why we want these 2 numbers is because if you go all the way back up to the top, there is our test statistic. Our test statistic is this ratio of the mean squares between and the mean squares within. Now, if you're crying a little bit because you're hearing about this, and I don't even blame you, it's so much to calculate. Don't fret. We will get this number from our calculator. So I'm just gonna reiterate to you that we will get this from our calculator. And what that ultimately means for you is all of this shenanigans that's down here, all of this stuff that just looks so ugly. We're not gonna do any of this. We're not gonna do any of this. We're not even gonna do any of this. But that's why I put the dot here. You do need to know the degrees of freedom so I can get FCDF to work. And other than that, you're gonna be in good shape. So all of this, I just feel like I have to show them to you as a teacher. And I get to use that whole, like, back in my day, I had to do this. And back in my day, I did have to do this. And it sucked. It was so long to do all of these number crunches. And I only had one of those, like, scientific calculators. And you can imagine if you make a mistake, just a little typo early on, your whole number is off. It was pretty cumbersome. And now we have these awesome TI-84s that do everything for us. And we've got technology that'll do everything for us. It's great. All right, so let's take a look at what the graph looks like. So I'm gonna scooch over here, and let's take a look at what our basic F distribution looks like. Again, it's skewed right, and the mean is the degrees of freedom within in ratio to the degrees of freedom within minus 2. All right, and so the mean, again, it gets closer to 1 as the degrees of freedom increase. So let me just give you a for instance and show you what I mean. Let's say for some reason the degrees of freedom within were 10. All right, I would have over here 10 divided by 8. All right, and as a fraction, that would be 1.25. Close-ish to 1. Again, not quite 1, but close enough. Well, let's say I had degrees of freedom of, let's go with 20. If it was 20, right, if my degrees of freedom increase, then this ratio will turn into 20 over 18. And let me get my calculator out. I don't have that one memorized in my head. So we'll go 20 divided by 18, and now we're looking at 1.1, right? So that number got closer to 1. And as the degrees of freedom increase, this ratio will get closer and closer and closer to 1. Which is why up top I said when the null is true, your F-test statistic should be close to 1. It won't necessarily be exactly 1, but it'll be close to 1. And especially as the degrees of freedom increase, that number is going to get that much closer to 1. All right, so the mean of the distribution is a fraction that gets closer to 1 as degrees of freedom increase. A good rule of thumb is that 1 will be close to the peak of the curve, so somewhere around here, all right? But it might be a little to the right of the peak. It's close to the peak, all right? As sample size increases, the shape of the F distribution gets closer to normal. So this is your basic F distribution. That's what most of them look like. But when you have a really small degrees of freedom, it actually can still look like the hyperbola. So again, these aren't color-coded like they are if you just download the PDF. When I print them out, they come out in black and white. But when your degrees of freedom between and within, you can see this first one are 1 and 1. You've got this hyperbola looking thing. But you can see here when we get down closer to the bottom, when your degrees of freedom between and within are both 100, meaning you have a pretty large sample, you can actually see the bell curve hanging out in here, right? And then about halfway through that, you see some of these look a lot like the chi-squared curve, right? They're very skewed right and unimodal. All right, but as degrees of freedom increase, the shape of the F distribution gets closer to normal. The same was true for chi-squareds as with Fs. So this will be your basic F graph. And I'll put this on your problems. I'll just photocopy it in there, or not photocopy it in there, but I'll basically draw that shape each time because your calculator won't draw the F distribution for you. So just be aware that most of the time, not most of the time, all of the time when we do these problems in this class, we're just gonna draw this one, okay? All right, so with that, let's flip the page and take a look at our first ANOVA together. All right, gang, here we go. Let's try and think about what is the variable in this problem. So the table below shows the lifetimes under controlled conditions of hours in excess of 1,000 hours for a sample of 60-watt electric light bulbs of 3 different brands. Assuming all lifetimes are to be normally distributed with common variance, test the hypothesis that there is no difference between the 3 brands with respect to mean lifetime. Use a 1% significance level. Okay, so as I look at this, I see the word mean. That's a great thing. I also see some units in here. All right, so in terms of what land am I in, I know I'm in mean land. All right, and my variable, I'll put that here, my variable. All right, if I look at all of these numbers, right, these aren't frequencies, these are actually data values this time. It looks like it's lifetime, right, and this is 16 hours, 15 hours, right, but this is hours in excess of 1,000. So this is lifetime of light bulbs. And it's in excess of 1,000 hours. And the units for this are hours. So I know that this brand 1 light bulb lasted 16 hours past 1,000, right? This one lasted 26 hours past 1,000. Okay, and I can also see I have 3 groups, right? So if I have 3 groups this time out, we're actually gonna say I have 3 levels. And anytime I have more than 3, it's time to run that F distribution. And let's just keep some of our vocab in mind from the front page. So anytime I know I'm gonna run ANOVA, I should figure out what is my factor and what is my level. So in this case, the factor, right, it's a categorical variable, right? How are the different observations grouped? And they were grouped by brand, right? We had brand 1, brand 2, brand 3. Okay. How many levels did I have? Well, I had 3 values to that factor. So for this problem, in example 2, right, we know k is equal to 3. So let me just take note of that. And also I note that I had 15 total light bulbs. It looks like they had 5 in each group. And again, you don't have to have the same number in each group. You have whatever you have. But so I know k equals 3 and n equals 15. So those are a couple of things for me to just keep track of as I move through this, okay? All right, so let's start writing up this hypothesis test. So step one is back. We're gonna define some mu's, right? So this is gonna be the true average lifetime, and then again, in excess of 1,000 hours for brand 1 light bulbs. And the units for this are in hours. Oh, I didn't need to put this in parentheses. I mean, you can, it's no biggie either way. I usually put the units in parentheses. All right, we got mu sub 2. I'm gonna do a bunch of quote marks. And mu sub 3. Okay. All right, so let me move this up so we have a little bit more space. I'll try and keep our data in view here. All right, so let's keep on going with this. So step 2 would be our null, and there's always equality in the null. So we would say mu sub 1 equals mu sub 2 equals mu sub 3. All right, and let's just get some gut feelings for this. Do we think this is true? So if I look at mu sub 1, if I look within, not mu sub 1, but within brand 1, it looks like the average is somewhere around like 16, 17. All right, that's what I'm looking at just numerically. Here, the average looks like it might be a little higher, like 20, 21, right? And this actually looks a lot higher to me, right? These are all pretty much larger numbers than brand 1. So I think this average would be closer to like 26, 27 if I'm looking at this. So do I think that all the means are equal? Do I think that if all the means were equal, if the null was true, would I see sample data like this? I don't think so. I mean, I'll go ahead, obviously, and we'll run the hypothesis test. But I'm thinking that at least 2 of the group means are not equal to each other. Like, I could see it being possible that these 2 are equal to each other, even though these numbers are slightly higher. I could see that happening just by chance, but the discrepancy between brand 1 and brand 3 looks to be extreme. So in terms of the alternate, all right, I'm gonna say at least 2 of the group means are not equal. Okay. So step 4, I'll put step 4, I'll go over here to just kind of, well, yeah, I'll go here to save some room. So 4 is our alpha level. I will default to 5% if not given one. Oh, but I was, it's off view, but I was given a 1% significance level. So we'll go with 0.01. All right, let's start checking some assumptions. All right, so if I take a look at my assumptions, I need independent random samples. That's what I'm looking for. All right, so let's see if we have independent random samples. Now, in terms of independence, do I think that the average lifetime for brand 1 light bulbs has anything to do with brand 2 light bulbs? I don't. Or brand 3. They are independent samples. I'll give you that. All right, now, was there any phrasing in the setup that told me I had random samples or that my samples represented my population? Let's just take a quick look through. I see normally distributed, I see common variance. I don't see anything about random samples. Okay, not a deal breaker. So I'll just take note that I did not have random samples here. Okay, for normality, let's see if we can figure this out, because the next assumption, the deal breaker one, is that the population at each factor is approximately normal. Well, I saw the phrasing up in there that normality was stated, all right? So I'm good to go there. Now, just as a side note, let's say it wasn't stated. If you remember back when you're in mean land, all the same rules apply. If the sample sizes are 30 or higher in each group, right, which they're not, we only had 5 in each group, or if box plots showed plausible normality, you could be good to go. Now, just to show you what plausible normality looks like, or to remind you, if you had your data in your lists, you could set up 3 box plots at the same time. So let me go ahead and do that here. This will be against 1. Let me get plot 2 going. And let me get plot 3, turn it on, and we'll go L3. Okay, let me make sure all of these are set up. So I have 3 plots on. They are all modified box plots, and I see L1, L2, L3 against 1. Great, so I'm gonna hit zoom 9. And if I take a look, all of these box plots, keeping in mind there were only 5 numbers, that this is all, they're all roughly symmetric with no outliers. So I could assume plausible normality just off of the graphs as well, okay? All right, and then the last assumption that we have to take a look at is, do these distributions have a common variance, right? So the normal populations have a common variance. Now again, it's stated in the problem that they have a common variance. So I'm gonna just check this off. Okay, but I also just wanna point it out here. If we look at the box plots, all right, a real like rough rule of thumb, if you look at these box plots, they're all about the same length. Like one isn't way longer than the other. If I was gonna try and measure it, although I don't know how effective this is about to be, yeah, my ruler's gonna stink. They're all, I don't know, 3/4 of an inch or pretty close to it. So since they all have the same length, right, the same, yeah, spread, you could say that it's very plausible they had common variances. And with all of this, there becomes a lot of question, like, well, what's the cutoff for having common variances? We're not gonna go into that. When it comes to chapter 13, I'm never actually gonna have you check the assumptions. I did it this time out because I'm a teacher and I felt like I have to, but I'm just gonna say, you don't need to do this for this test only, okay? So checking assumptions not needed only in chapter 13, right? Every other chapter, it's gonna be needed. All right, so with that, let's keep moving on. Step 6, which distribution am I on? I'm on the F distribution. Okay, all right. Which test am I about to run? I'm about to run one-way ANOVA. Okay, and for degrees of freedom, this is going to be a little bit more convoluted. There's 2 formulas for degrees of freedom. So we need to find the degrees of freedom between and the degrees of freedom within. So I need the degrees of freedom between, and I need the degrees of freedom within. Okay, so let me start moving this up just so I have a little bit more space in my write-up. All right, so for degrees of freedom between, we have the formula k minus 1, and for within, we have n minus k. Well, if you remember, we had 3 levels, so I'm gonna go 3 minus 1, which is 2. And here, for n minus k, I had 15 light bulbs, all right, but I had 3 groups, so 15 minus 3 is 12. All right, so ultimately, if we wanna just write this up more succinctly, I would say the degrees of freedom between are 2, and the degrees of freedom within are 12. Okay, great. Step 9 is our test statistic. All right, so F, right? We have that formula, right? It's mean squares between to mean squares within, and we want it to be close-ish to 1 if the null is true. All right, or I should say if the null is true, it should be close-ish to 1. So we're going to go mean squares between in ratio to mean squares within. All right, and again, these are the average square of differences between the 3 groups and the average squares of differences within one group. Now, that ratio, again, if you're feeling bold on a Friday night, go crunch this. It's not the greatest time, but it is its own exercise in just number crunching. So you can move through all of these formulas and finally get these sum squares between and within, put them in ratio to the degrees of freedom between and within, and get your mean squares between and within. But ultimately what we're trying to say is if the null is true, if the means really are equal to each other, then the differences between groups should be the same about the differences within one group. All right, because if the means are equal, the variance between groups or the change between groups should be the same as the change within any one individual group. All right, so now you can take a leap of faith with me, all right? And I'm just going to tell you this is 15.5, okay? We'll come back to this in a moment, but you're going to take a leap of faith with me right now. So for step 10, just say, hey, I know it's 15.5. And the reason I want you to take a leap of faith with me is I don't want to show you how you can do this on your calculator just yet. I want to talk about how we get the p-value just to make sure we have a certain concept down. So if I want to get the p-value, okay, the p-value, again, it's a probability. You owe me a letter, a symbol, and a number. Our letter is always our letter from step 6, so we have f. As I mentioned before, mean squares, or the f distribution, or the f test statistic, excuse me. I keep mincing my words. I think mixing my words. Maybe mince? I can't even get that phrase right. Okay, here we go. So every test statistic you get in step 9 will be positive. So, or steps 9 and 10. It's constructed to be positive. This word right here, the S here, means squares. Any squared number in math is automatically positive. So we will only ever look at right-tailed tests. And you always use the number that you picked up in step 10. So as we start to go through this, right, let's now use FCDF. We're going to go 15.5, 1E99 for infinity. And here's where your degrees of freedom come in. So you're going to go mean squares between, and then within. So we're going to go 2, 12. So the FCDF needs both of those degrees of freedom, which is why out of all of those formulas that were on the previous page, the only thing I bullet pointed was those degrees of freedom, right? So out of all of these formulas, the only ones you really need in order to get FCDF to work are these 2 degrees of freedom measurements, okay? So with that, let's go see what we have working here. So FCDF is in the same spot that every distribution is, and it's a little further down, right? We've done the normals, we've done the t's, we picked up the chi-squareds, and if you go below it, there is FCDF, so it's option 0. So let's do 15.5, 1E99, and then 2, and then 12. All right, so let me go ahead and hit that, and then we've got, okay, it's not 4.72, right? I've got e to the negative 4, so our p-value is 0.000472. All right, so we've got 0.000472. All right, now let me scoot this up just a little bit more so that I can write my graph and my summary as we get through this. So for step 12, let me get my ruler. We're gonna make our little FCDF, or our F distribution. All right, so it's gonna look something like this. Okay, I'm gonna label this is my F distribution. All right, 1 is somewhere close to the peak, kind of hard to tell, no problem there. Now 15.5 is gonna be way out here. And I know it's gonna be way out there because look at my p-value. I only need to shade 0.00472 of the area under my curve. Excuse me. So I'm not really shading a whole lot. Okay, and then it's time for our conclusion, right? Our standard, do we reject or do we fail to reject? So look at your p-value, it's much less than your alpha. Your alpha was 1%. So because our p-value is less than alpha, we reject H0. right? There is sufficient evidence that at least two of the group means are not equal. Or really, we could just say there is significant evidence of a difference in mean lifetime between the three brands of light bulbs, right? So where I'm getting the phrasing here is you have a couple of options and you can decide what's best for you. You could actually just write the phrase from the alternate. That's fine. I don't even necessarily like doing that because it's got no context to it. I would take this phrase right here. We have sufficient evidence, not that there is no difference, of a difference between the three brands with respect to mean lifetime. So I'm going to use that phrase that was presented to me in the problem so I don't have to come up with my own phrase. So let me go all the way back to here, get this kind of in focus. There we go. So we have sufficient evidence of a difference in mean lifetime between three brands of light bulbs. All right, so all we're saying is these three brands of light bulbs, they don't perform the same. All right, at least one of them is different from the other, or you say at least two are not equal to each other. And I'm guessing it's brand 3, right? Brand 3 looked like if I was going to go buy a brand of light bulbs, I should go pick up brand 3. All right, so with that, we're gonna try a couple more examples of ANOVA. All right, see you in a bit. Bye. Hey Math 43, let's take a look at how to run ANOVA on our calculators. So take a moment and get your data put into your lists. I have it here. And just to remind you, if you did ever want to check your assumptions, if you wanted to check that normality assumption, you could set up your stat plots and have all three plots on and just hit zoom 9 and see that those box plots were roughly symmetric, right? Keeping in mind, we only had 5 data points. So each of those data points is going to make up one of the numbers in the 5-number summary that you need to make a box plot, right? Because you needed min, Q1, median, Q3, and the max. So they're all displayed. And so they all look roughly symmetric. I'll give you that light bulb brand 1 and 3 look a little bit skewed right. But really, when you only have 5 data points, these are great. And the lengths of each of them are around the same. So that's why we would say they have the common variances. All right, so here's how you can run ANOVA. So you guys took a leap of faith with me when I told you, hey, that number was 15.5, that test statistic in step 10. And then we were able to run FCDF and get that p-value. But I want to show you how your calculator can help you through all of this. So let's go ahead and hit stat, go over to test, and quite literally the last test that the calculator, the TI-83 or TI-84 can do is called ANOVA. So you could scroll all the way down to H, or you can just scroll up and find the one that says ANOVA. So go ahead and get to H one way or the other and hit enter. And this has a very different interface than all of the other calculator, the hypothesis tests. So what you're gonna do here is you're gonna tell it which lists to look at. And for this problem, we had 3 lists. We had one in L1, or I should say we had 3 lists. We had data in L1, L2, and L3. So put those in and separate them by commas. All right, and then we're gonna hit enter and a whole bunch of stuff is gonna pop back out. Right, so there you're looking at your F test statistic of 15.5. There's your p-value, and again, your p-value is not 4.72. Your p-value is a probability, right? It's the probability that if the null were true, what's the likelihood we would get sample data like this? Just by chance. Just because something has to happen. So what's the likelihood of what we saw happening actually happening? And this is saying our p-value is basically 0, right? If the null was true, we would never see data like this. So if all 3 of those light bulbs perform the same way or have the same average lifetime, we would never see sample data like this. Now your calculator, for whatever reason, calls the between data, they use the word factor. And then for the within data, they use the word error. I don't know why Texas Instruments programmed it that way. Most people say between and within, but okay, they're gonna call it factor and error. So you see the degrees of freedom between is 2,
right? We see the degrees of freedom within is 12. These are our sum squares. These are our mean squares for both the between and within. And if you don't remember me talking about sum squares or mean squares, I can just scroll back up here. Remember all those formulas I said were like a good time for me in college, but kind of stink. So all those sum squares and mean squares, those are all of the statistics that are popping back from one-way ANOVA. Okay, so we got that going on. Now the one thing that this hypothesis test function doesn't do is it doesn't draw the graph for you. Right, so in previous ones we had the graphs drawn for us. So we're not really sure if we have the hyperbola looking graph or we have the unimodal skewed right one, or is it actually looking more like the bell curve? We don't know that from the calculator options in the ANOVA test, but there is a way to do it. It's not the greatest. I don't use it that often because I'll just go with your basic unimodal skewed right curve, but I do want to show you this option. So if you want to make a graph, here's how you can do it. So let me clear all of this out and I'll clear my key press history. So we're starting fresh. So hit second and vars, all right, to your distributions, but now go over to the draw menu. All right, so we're gonna shade, and we're gonna shade the F distribution. So you can always shade norm, shade T, shade chi-squared, but you have that draw command in the hypothesis test options that does it for you. So let's go to option 4, okay? And here's what you can do. You can enter in your test statistic, right? You wanna go from your test statistic to positive infinity, degrees of freedom between, degrees of freedom within. So it's basically the same calculator function or the same 4 numbers we would have popped in for FCDF. So I'm gonna do 15.5, and then I'm gonna go to positive infinity, and then I'm gonna go to 2 and 12. Now in a moment I'm gonna hit enter, and it's gonna be a mess, and I'm gonna show you how to fix the mess, but I want you to see that it's gonna be a mess. All right, so I'm gonna hit enter. You're gonna see the 3 box plots still hanging out there, and you can see my calculator thinking, right? I don't know if you saw that, like that repeating vertical bar up there. And you don't see anything, right? Ultimately at the end of this, all it tells you is the p-value, and you don't see a graph. And the reason why is because your window right now is set for your box plots. So it's set for all of that data that we got given to us in this table, right? You can see the min is 11, the high is about 32, because if we take a look at this data, the lowest number in here overall between the 3 groups was 13, and the highest was 31. So you see your window going a little bit below that number and a little bit above that number. Okay, well imagine you wanted to shade this F curve, all right? This F curve, if you look at the x-axis, and I know we labeled it with the letter F, but it's going from 0 to about 15.5. That's nowhere in this range, right? We need to lower my x min to 0, and we need to bump this up to maybe 20. Maybe we'll go a little bit to the right of it. And on the y-axis, what you need is probabilities, because every time we have a graph, our y-axis is always probabilities. Well, probabilities go from 0 to 1, right? Proportions go from 0 to 1, relative frequencies, all of that, probabilities as well. I can leave this as negative 0.05. I can give myself a little bit of a buffer below the x-axis. But I'm gonna bump this y max to 1, okay? So once you've adjusted your window, then go back, all right? And now I'm gonna just call up that function I did before by hitting second and enter. Now when I graph it, oh, you know what, I'm just remembering. I'm gonna graph it, but I think I did not turn my plots off, right? I should have turned them off. Yeah, if I look, sorry about that. Before we go back and graph it again, let's turn our box plot to off. I would like to turn all 3 off at the same time, so I'm gonna use option 4 here and just say, hey, turn them all off. Ooh, and now I am making a mess. So this is an example of what not to do. So let me clear this off. All right, first thing I'm gonna do is I'm gonna turn my plots off. So let me rework this and turn my plots off. So now I'll hit option 4, I'll hit enter, and it's done. If I go back into those plots, you can see they're all off now, and that was just a quicker way for me to do it. All right, now that I've turned my plots off, now I'm gonna go back and I'm gonna do that shade F, 15.5, positive infinity, degrees of freedom between, degrees of freedom within. Now when I hit enter, you're going to see a better looking x-axis. There's probabilities on my y. Here comes my F distribution. It looks more like the hyperbola one rather than the skewed right unimodal curve. So we're on one of these hyperbola looking ones before it converges before that value on the y-axis drops to the origin down here. Now I don't see anything that I've shaded because my p-value was essentially 0. I'm fine if you leave me with this general looking F distribution. Like I said, I don't really use the shade F that often. It's not my favorite thing in the world. And once you get to ANOVA, really we're just looking for the p-value and what the conclusion would be. And like I said, this particular function looks more like an exponential than a standard graph, or I would say a hyperbola more than the standard graph that you've seen so far. So I'm fine with whichever one you want to draw me. But I did want you to see that option in terms of how you could run or how you could get that graph if you wanted it. But the bottom line for all of this, if you want to do ANOVA, let me clear this out. We're going to run it one more time, right? Stat, we go over to test, it's the bottom one, and then give me all of your lists. All right, in this case, we had 3 lists. So I'm going to put them all in, hit enter, and then go ahead and read those first 2 numbers, right? This is step 10, this is step 11. The degrees of freedom between the factor and the error, which we mean between and within, are step 8. All right, so that's how you use your calculator in one-way ANOVA. All right, thanks guys, I'll see you in a few, bye.